Hi there. My Android OS internals version 14, from apps down to kernel, Udemy course is now available. In this course, you will learn how to run Android in the cloud, create system services, solve SE Linux errors, and debug native crashes. Navigate to this address or scan the QR code to sign up for the course. So let's get started. Before we can download, build and run the Android open source project, we'll need to create a virtual machine in Google Cloud. We are using Google Cloud, but you can use an Ubuntu 20.04 on your machine as long as you have at least 16 GB of memory and 500 GB of hard drive. Let's navigate to the Google Cloud console. Next, let's click on Select a Project and then click on New Project. Enter AOSP as project name and click Create. Once the project is created, we can click on Select Project to enter the AOSP project. In the search bar, search for Google Compute Engine and select it from the list. Because this is a new project, we need to enable the Compute Engine API by clicking Enable. Before we can continue, we'll need to set up a new Google Cloud account. We'll select a country. Next, we'll set up a payment method because nothing in life is free. If everything worked, we can see in the notification menu that the Compute API service was enabled successfully. We can go back to the Compute Engine screen, where we now see the VM instances page, which is currently empty. To be able to connect to our Google Cloud account and set up a new VM from the command line, we'll need to download and install the gcloud CLI for our machine. There is an install file for most operating systems. I am running on Mac OS, so I will select the Mac OS tab and download the Apple Silicon gzip file. Once downloaded, unzip the gzip file and run the install script. I already have it installed, so I will go to the next step to connect my new Google Cloud account to the gcloud CLI by running gcloud init. gcloud shows that I am already logged in as another account. I will need to choose option number 2, create a new configuration, so I can connect to the new account. I will name the new configuration AOSP. I will select option number 2, log in with a new account. The browser will now open, and I will need to select the Gmail account with which I've opened my Google Cloud account. I will need to authorize Google Cloud SDK to access my Google account. Once the accounts are connected, I can go back to the terminal and see the list of projects. The first project is the project I have made, so I will select it by typing 1. Lastly, I will need to configure a default compute region and zone. I live in the West Coast, so I will choose the US West 1 Region B zone by typing 11. Now we are ready to create our virtual machine so we can host the Android open source project in order to build and run the Cuttlefish device. We'll start by creating a compute disk named AOSP disk, based on the Ubuntu 20.04 LTS image with 1000 GB of hard drive space. The exact commands will always be in the resources folder. Next, we'll create an image named AOSP image using our AOSP disk as the source disk. I will also need to specify the disk's zone, and in my case I set it to US West 1B. Since this image must support virtual machine extensions, we need to include the Enable VMX license. Finally, we'll create a VM instance named AOSP1 based on the AOSP image. The created VM has been assigned an external IP, which we will use shortly, to connect to the VM's terminal console via SSH. Storing data on Google Cloud incurs costs, which are based on the amount of storage you actually use, rather than on pre-allocated disk space. For instance, storing 500 GB will cost approximately $10 per month. Running virtual machines also costs money, and the charges depend on the allocated CPU and memory. we'll use the N1 standard machine type. When downloading the source code, we can select the N1 standard 1, which costs about 5 cents per hour. The minimum required machine type for building Android is the N1 standard 4. However, using a higher CPU core count will speed up the build but also increase the costs. That's why it's important to shut down your VM after use. Let's return to Google's Compute Engine and refresh the VM Instances page. We should now be able to see our newly created VM. If we click on the SSH button, we can access the terminal through our browser. We just need to authorize our browser for SSH access. Now that we are logged in, we can run the ls-l command and see that there is nothing in the user's directory. We ensure that we have at least one CPU core that supports hardware virtualization by running the following grep command. Let's return to the VM Instances web page. Next, we will edit the VM instance, so we'll need to stop it first by clicking the menu and selecting Stop. We also have the same button here, which is useful if you want to stop a selected group. It might take a bit of time to stop the VM, but once it has stopped, we can click on its name to view the details. Let's click on the Edit button. Let's scroll down to Machine Configuration. We can see that the VM is running on the N1 Standard 1 configuration. The N1 machine is based on an Intel CPU. Intel CPUs support nested virtualization, which is required for the virtual Android device that we will build and run in this course. We will build the Android OS with 16 virtual cores to speed up the build process. So, let's test whether we can boot it up successfully by selecting the N1 Standard 16. If you wanted to customize the exact combination of cores and memory, you would click on the Custom tab. I usually add more memory for 16 cores because 60 gigabytes is too low for that many cores. I will not set it just now, as this requires submitting a request to Google to increase the quota, which will probably get denied until the first billing cycle is completed. Before we click Save, we'll scroll down to the SSH key section. We want to add a new public SSH key so we can access our VM from the console via SSH. Let's switch back to the terminal. We are going to run the SSH keygen command and specify that it should generate an RSA key type. For Windows users, I've provided instructions on how to install OpenSSH, which includes the SSH keygen executable. Back to the SSH key generation. I will name the key file AOSP. Since I already have a key with that name, I am going to cancel this and try a different name. You can choose any key name you prefer, but I am going to use 8man tech. I left the passphrase field blank, so the key is now ready to use. It consists of a private key file named 8man tech and a public key file named 8mantech.pub. We'll print the content of the public key file by using the cat command. In Windows, we'll use the type command instead of cat. The last part of the public key indicates the username. So if you would like a different username, make sure to change it when pasting it into the SSH key box. Let's copy the public RSA key and return to the VM web page. We'll paste the public key as a new SSH key and click Save. In the same VM instance, we'll scroll down to the Network Interfaces section and click on the NIC0 interface. On the left panel, we'll select Firewall to access the firewall policies. We'll select Create Firewall Rule. We'll name the firewall rule Allow CF, where CF stands for Cuttlefish. We'll scroll down to Protocols and Ports, check the TCP box, and paste the following list of ports to allow access to Cuttlefish. Refer to the course's resources to copy the list of ports. Next, we'll check the UDP box and paste the following range of ports. Before we can create the firewall rule, we'll need to scroll up to the targets and select All Instances in the Network to set it as a global rule. For source IPv4 ranges, we'll put 0.0.0.0/0. Finally, we can click Create to create the firewall rule. We can now see that the new firewall rule has been added to the list of firewall policies. Let's return to the VM Instances page and start our VM instance. Once we get an external IP, we can click the copy icon to copy it to the clipboard. We'll go back to the console and validate we have the 8-man tech private key. Now we can run the SSH command by providing our private key as the identity file, followed by the username, the @ and the machine's IP address. We should be able to successfully log into our VM. We can run the following grep command to check the number of virtual CPU cores. Finally, we can stop our machine because we will be downloading the Android open source project, and there is no need for so many CPU cores for that task. In this video, we'll download the Android source code project into our VM. But before we turn on the VM, we can adjust the CPU cores to meet our needs. So let's click on the VM name and then click the Edit button. Scroll down to Machine Type and select the N1 Standard 2. This machine type does not have enough resources to build the Android OS. It is only sufficient for downloading the source code. If you want to build the Android OS, you can choose the N1 HiMem 8. Make sure to click on Save to apply the changes. Let's start the VM by clicking Start Resume. Go back to the VM Instances page. Give it a minute to boot up, then copy the external IP address by clicking the copy icon. Let's use the previous SSH command, replacing the IP address with the one you've just copied. We should now be logged in. I'll print the virtual CPU cores. Before we can continue, we'll first update the list of package indexes by running the sudo apt getupdate command. Next, we'll install the required packages. Remember, all the necessary commands can be found in the course resources. To download the Android source code, you must install the repo tool. First, we'll create a bin directory. Next, we'll execute the following commands, which are copied from source.android.com. We'll create a new directory named AOSP, and we'll cd into that directory. We are running repo init to download the AOSP repo manifest from the Android 14R21 branch. This course was created in February 2024, and this was the latest branch available, which is the one used in this course. After repo init is complete, we are now ready to download the source code by executing the repo sync command. This command uses the J2 option, which specifies that it should use 2 download threads. The source code download is expected to take a couple of hours to complete. Once the download is complete, we'll view the content in the directory using the ls-l command. We will build the Cuttlefish device, which is located in the device directory. The course will also cover topics in the frameworks directory, such as the SDK. Additionally, the code that we create in this course will be placed in the vendor folder, which we'll create soon. We are now ready to build the Android Cuttlefish device. Please note that if your VM has less than 16 GB of memory, you will need to make a change. To do this, first turn off your VM and wait until it's completely off. Then, click on the VM's name and select the Edit button. Scroll down to Machine Type and choose the N1 HiMem8 preset. Click Save and start your machine. Go back to the VM Instances screen and wait for your VM to boot. Click on the Refresh button to see the external IP of your VM. You can now copy the IP address to log in via SSH. If I can't log in due to a warning that the remote identification has changed, I have two options. I can either delete the known hosts file or edit it to remove the line containing the VM's IP address. I will delete the file and try logging in again. I will cd into the AOSP directory. The next two commands are required each time I open a new terminal. The first step involves loading the AOSP environment variables into memory by executing the command source-build env-setup.sh. The second step is to run the launch command, which displays the possible build configurations. In this course, we will build the Cuttlefish device, which is listed as AOSP_CF. You have the option to build a phone, a TV, Android Auto, or a foldable device. I will choose to build the AOSP Cuttlefish x86 phone by entering 21. I can now see the loaded build configuration, which includes the platform version, which is Android 14, the target product and build variant we chose, the build ID, which should match the checkout tag. We are now ready to initiate the build process by executing the make command. We'll use 8 of the virtual cores, hence the J8 flag. The build time is directly influenced by the number of CPU cores and the amount of memory allocated to the VM. This VM clean builds the Cuttlefish device in 6 hours and 42 minutes. Listing the contents of the AOSP root folder reveals a newly created directory named out. The out folder is where the build system outputs the results of the compilation process. Deleting the out folder is equivalent to performing a full clean build. Let's navigate to the out target product directory, where the build system creates a folder for each target device we build. Our Cuttlefish codename is VSOC_x86, so we'll navigate into that directory. Upon listing the contents of this folder, we see the output images from the build. The largest image is the super image, which contains the system, product, vendor, and ODM images. Before making any changes, we should create an instantaneous snapshot of the image. In the Google Cloud Console, we'll navigate to the Snapshots tab and click Create Snapshot. We'll select the source disk, select Instant Snapshot, and click Create. Let's return to the AOSP root directory by entering croot. Before we can launch the Cuttlefish device, we'll need to execute the following commands, just once. First, we'll copy the sudo apt install command and paste it into our VM's console. Next, we'll copy and paste the git clone command. Now we'll execute each one of the install commands for the required Cuttlefish Debian packages. We'll copy the usermod command, which grants the logged-in user access to the kernel virtual machine, the network, and the GPU. For the changes to take effect, we will need to reboot the VM. Once the VM has fully booted, you will be able to log in again. Once logged in, we'll cd into the AOSP directory. As always, we'll execute the source-build env-setup.sh command. Next, we'll run launch21 to load the Cuttlefish x86 phone variables into memory. Since we've already completed the build and installed the Cuttlefish Debian packages, we can launch the nested VM by running launch_cvd. Once the virtual device has booted successfully, you can view it in your browser by entering the IP address of your VM, followed by port number 8443. You can disregard the warning and click Proceed. Now you can connect to your virtual device to view and interact with it. Let's return to the terminal. You can terminate the VM by pressing Ctrl+C. Executing ADB devices reveals that no Android devices are connected. However, you still need to run stop_cvd to close the socket. You can run launch_cvd without blocking the main thread by appending an ampersand at the end. You can now run ADB devices to see your device listed among the connected devices. Executing ADB shell will log us into our Cuttlefish console. We can execute su to switch to the root user. Due to the extensive output from the launch_cvd command, it's advisable to open a new terminal and log into our VM. Once logged in, we need to repeat the same two commands: source build env-setup.sh and lunch21. Now we can run ADB shell again. Executing the id command shows that the current user ID is shell, and it belongs to these groups. It also has the shell SE Linux context. After running su and id again, we observe that the user ID and group ID have changed to root, while the SE Linux context is su. As a root user, I can list the files in the root directory. Executing logcat-ball displays the user space logs in the system. Running the dmessage command outputs the kernel logs. To exit the superuser, type exit, and to leave the Android device, type exit again. We can stop the Cuttlefish device by entering stop_cvd. If you're finished with the VM for the day, you can turn it off in the VM Instances tab. In this lecture, we'll install the Ubuntu Desktop Graphical Interface. First, we'll install Chrome Remote Desktop on the VM. We'll use the wget command to download the Chrome Remote Desktop installation package. Next, we'll execute the sudo apt get install command to install the package. Now, we'll run the sudo apt get update and upgrade commands. Next, we'll install the Slim Display Manager. Following that, we'll install the Ubuntu desktop environment, which may take some time to complete. After the installation finishes, reboot the machine. Once the instance is back online, SSH into the VM. Finally, start the Slim service using the provided command. Switch back to your computer and navigate to the Chrome Remote Desktop website. Click on Setup via SSH. Click Begin. Click Next. Click Authorize. Copy the Debian Linux command. Go back to your VM and paste the command. Enter a 6-digit PIN. Once the host starts successfully, return to your machine and click on Remote Access. You should see your VM listed under Remote Devices, and you can now click to connect. Enter your 6-digit PIN. Click OK. Click Cancel on the Authentication Required dialog. Continue clicking Next until you have completed the onboarding process. In this lecture, we'll install and configure the Android Studio for Platform IDE. Click on Activities and type to search the terminal application. Open the activities again and start Firefox. Search for Android Studio for Platform and click on the first link. Click on the Download button and accept the terms and conditions. Once the download has finished, CD into the Downloads folder. Run the sudo dpkg-i command to install the package. After the installation completes, you can start the IDE by executing the Studio shell script. Click Next to initiate the setup wizard. Accept the terms and conditions. Once the setup is complete, click on Import ASfP project. Set the repo checkout path to the root AOSP folder. Your build target is the one you selected when building Cuttlefish. I've selected AOSP CFX86 phone user debug as my target, so I will use that as the build target. For the module path, I will select the following modules: Device, Frameworks, Hardware, Packages, and System. If you plan to work with other directories, you can select those as well. Click Finish. The sync process will take a couple of hours, but this is a one-time operation. You are done installing and setting Android Studio for Platform. In this course, we will develop a complete data pipeline starting from a persistent application platform service to a kernel driver. The kernel driver we'll connect to is the CPU scaling governor, a driver responsible for managing the frequency of the CPU to balance performance and power consumption. We'll begin by creating a CPU HAL, hardware abstraction layer, interface definition file using AIDL, Android Interface Definition Language. The CPU HAL will define the functionality a HAL service implementation will provide for external applications. Next, we will develop a CPU HAL service that implements the interface defined in the AIDL file. This service will execute code that opens the kernel driver, read its value, and write a new value. The service will be configured to launch at startup and will continue running as long as the device is operational. We'll develop CPU HAL tester executable that uses the CPU proxy class to connect to the CPU service and invoke remote functions. The tester code will not directly access the kernel driver. Instead, it will rely on the CPU service, which has privileged access to perform these operations. Finally, we will develop a persistent application containing buttons for each supported CPU scaling governor. This application will also use the Java proxy class to establish a connection with the CPU HAL service. Pressing one of these buttons will change the CPU scaling governor as specified.